I advertised that we were going to use the criterion for ampleness and wall crossing to show that there is a smooth, complete toric variety which is not projective. So here it is. So what we're going to do, and I've cheated by having everything prepared, I take the fan for P1 cross P1 cross P1. So that fan has as its maximal cones. The three-dimensional cones are just all 8 orthents, right? You guys are with me on this. So P1 cross P1, P1 cross P1 is this, and P1 cross P1 cross P1 I add up and down, right? So, and then what I do is I subdivide the first orthent, so I'm going to subdivide this thing, and the subdivision is right there, E1, E2, E3, and the subdivide is this. And you can check, smoothness is local, so if you check, this is a smooth fan. Okay, everybody's with me so far, all right? So now what we're going to do is we're going to play a little game. So, and here's the other rays in this fan. So the first thing we're going to do is we take D equals summation A rho D rho and Cartier. And what I want to do is I want to make an assumption, and I have to justify it. I'm going to assume that the coefficients AE1, AE2, AE3 are 0. That is, that the coefficients on the rays right here, and right here are 0. So the way I can do that is what I want to do is find some character, a global thing, that I can add to my divisor that cancels those rays, right? So if I do that, I'm allowed to modify divisors by adding global rational functions, so that's what I want to do. So how do I do that? Well, the thing is that since I'm Cartier, I just can take the character, M equals minus A E1, that's this coefficient, minus A E2, and minus A E3. Again, there's some bad notation here because this AE is simply the A here, right? This is not related in any way to my A that's over here. You guys are with me, right? So these AE1, AE2, AE3 are the coefficients for those rays, and I'm going to take minus on those things, right? This is a character, right? These are just integers, and I've taken a character. And so the point is that now, what's the divisor of chi of m? Right? Well, the divisor of chi of m on E1, I'm just going to get exactly, when I look at the coefficient on D1, let's say restricted to D1, is exactly going to be, what? It's the minus AE1, right? That's exactly how we get it. And so that's going to cancel this is the minus AE1. And cancels that part of D. So we're allowed to assume can assume that those coefficients are 0. That phi sub D of E1 they're linearly equivalent, right? So what? So now what we want to do is we check our ampleness criteria, AMPLE. So what do I know? I claim that phi sub D of E1 plus B is greater than phi sub D of E1 plus phi sub D of B. Why? This is a wall condition, right? So the E1 plus B, this is a wall, I've got a wall condition here, so when I cross this wall here, I get that this, the phi sub d of E1 plus B, has to be greater than phi sub d E1 plus B. This is a wall inequality. But our assumption was that phi sub d of E1 is 0. So I have that. This seems pretty innocuous. I've just checked one wall inequality. On the other hand, and this is the way things are set up the way they are, what is E1 plus B? There's nothing toric going on here. E1 plus B, so B is 1, 2, 1. So E1 plus B is 2, 2, 1. This is equal to 2, 2, 1. You guys are with me, right? I'm just actually using the coefficients here. And that's the same thing as E2 plus A. Let's check. A plus E2, yeah. So this is equal to E2 plus A. So these are equal. That means phi sub d has to be equal on them. Phi sub d is just a functional, right? But then what do we know? This is also a wall condition. So I get that, this is, which wall is this? E2 plus A. This is going to be greater than phi sub d of E2 plus phi sub d of A, and this is 0. So this is bothering me a little bit. So let's see here. So something is wrong. E1 B equals this, phi sub d of E2 plus A. Oh, E2 plus A. Oh, stupid. Well, okay, what did I do wrong? Help me out. Somebody, what did I do that was wrong? E2 plus A is what? It's actually one of the rays, right? So I'm going to have an equality there. This is an equality here, because that's on my ray here. So this is an equality, this is 0, and so what I get, chasing through, is phi sub d of A is greater than phi sub d of B, right? So this gives me phi sub d of A greater than phi sub d of B. So what do you think I'm going to do now? We just cycle around. So I got phi sub d of A is bigger than phi sub d of B. I continue this process and I cycle around, which is going to be phi sub d of B. If you just run exactly the same argument here, this is going to be greater than phi sub d of C, which is greater than phi sub d of A. Contradiction. So what's the point? The point is that this is the criteria for an ample divisor. I get a contradiction. I can't have any ample divisors. And if I can't have any ample divisors, that means that there's no maps to projective space. So I think this is one of my favorite examples in the book, because I don't know, I guess your intuition maybe when you're first learning algebraic geometry is, oh, projective varieties, they're just these nice smooth compact things. And then when you take abstract smooth varieties that are still, complete, which is an analog of compact, you'd think, oh, well, they're all projective. And here's a nice example of a toric variety. It's smooth and complete, but not projective. So, but that's not so bad, because we now have the toric Chow lemma. So what I can do, so even though this was not projective, I can refine my fan in such a way that I get a projective variety that is, that I get a refinement such that it's projective. And remember, what this means is that we have maps, right? So when I refine the fan, I get a corresponding map of toric varieties. So that's the end of 6.1. 6.2. These are fans and base point free divisors. Def. So a generalized fan is a collection of rational polyhedral cones. So we're dropping the strongly convex, right? So we have a collection of rational polyhedral cones, we've dropped the strongly convex. If P is a lattice polytope, not dropping the full dimensional aspect of the lattice polytope. C sub V is the cone. P intersect M minus V, contained in M sub R, where C sub V dual of sigma V is C sub V check. Then we get proposition. And I'm going to do an example in 1 second. So sigma sub P is the set of cones sitting inside a vertex cone, the element vert P is a generalized fan, and with minimal cones are the span of M minus M prime element of P intersect M. And we dualize that. And this is a fan if and only if it's a full dimensional lattice polytope. Fan meaning strongly convex rational polyhedral fan. So if this leaves you cold, which it should, I want to do an example right away. So let's take a look at something. So, or actually before I do an example, I want one more little quick definition. Prop. This is the one we'll do an example of. If D is base point free with polytope P sub D, then this is on some toric variety X sigma, so D came from toric variety. If E is a vertex of P sub D, and sigma equals CV check, sigma element of sigma n, M sigma equals V. This is a description of my sigma sub V's, and B, this is the point really, sigma refines sigma of P of D. So what's the point of this? Let's take something that's a base point free divisor that doesn't have a full dimensional polytope. So 6.2.6. If we take on good old H2, 1, 2, 3, 4, we take D1. And we check that P sub D1 is just this. So I'm not going to write out all the local conditions. At this point, you guys can do this as an exercise. So polytope, the point is that the polytope's not full dimensional, right? I get a one-dimensional polytope. And what do we get when we look at the vertex cones? Here's V1 and V2. This is sitting inside, remember, M of R, it's two-dimensional lattice, right? So this is really smart to do an R2. And so sigma V1 check, sigma V1 is going to look like this. Sigma V2 and so what's the point is that this fan refined by the fan of the Hertzberg surface, right? So my fan is just basically this half space and this half space, right? So my fan is, and so what did I do when I refine it? I've subdivided this cone and I've subdivided this cone, so I get a refinement. So that's an example of this theorem at work. And then actually, I think the two most important theorems in this section are 6.2.7, which is that if I have toric morphism, and D2 is a T invariant divisor on x of sigma 2, then there exists a unique d1 on x sigma 1 such that O sigma is the pullback. So toric morphism, and I have a toric T invariant divisor on the target space, then I can pull it back to a unique divisor on the source space. And 6.28, d base point free on x sigma complete with x sub d, then the refinement sigma of sigma sub p of d induces a proper toric morphism from x sub sigma to x sub p sub d phi, and furthermore d is linearly equivalent to phi star of d of p of d. So all that this is saying is that basically there's a nice correspondence when you've got toric morphisms between divisors on the source and target space, so you can pull them back. So, and these are all relevant to this sort of, I guess, the notion of what's happening when we subdivide things. So now we're going to switch gears. That's the end of 6.2, and now I want to talk about some things that you probably have heard about in other algebraic geometry courses, and they might have seemed to be very high-powered things. So the Neff cone and the Mori cone. And in the toric case, as we've seen for just about everything, the Neff and Mori cones have very, very nice and concrete descriptions. And it's even, well, they're nice and concrete descriptions for all torics, but they're even better in the simplicial case, which is what the last part of what we do this morning will be. All right, so bear with me for a bit because we've got some definitions. So here we're going to be assuming that x is normal and C is a complete irreducible curve. Definition. So the idea, let me maybe say a few words before we get going. So the idea is we want to have an understanding of, just like we had this nice toric criteria for when divisors are ample and base point free, the set of all, and this is in general, not just toric, the set of all divisors that are Neff and ample and very ample, this is, if you remember, there's a famous theorem of Mori that says essentially there's a cone, which is not typically polyhedral, that captures all these, the Neff divisors, and that cone actually gets cut in half by the anti-canonical divisor. So on one half of the cone, it is actually rational polyhedral, but on the other half, it's like an ice cream cone. And so what's going to happen in the toric case is that, in fact, it's going to be a rational polyhedral cone. And the way that you get at this is there's a sort of duality that's the pairing between divisors and curves, right? So if you think very naively, and so of course there's a lot of work that you have to do technically, but if you take a curve, which is one-dimensional, and a divisor, which is given by a codimension one variety, and you intersect the two, you should get a finite set of points, right? And so what you want to do is take that naive notion of an intersection pairing and then fancy it up. And that's what we're going to do. And then we'll see that there's a beautiful relation between the Neff divisors and the Mori cone. And the Mori cone is a set of curves that satisfy sort of a similar positivity property. So that's the big picture of where we're going. So the first thing to do is to define this pairing. So d.c. So d is going to be, and this is, again, right now this is not toric. It's the degree of phi star of OX of D, where this was just a complete curve. It wasn't a smooth curve. So what we do is we take a normalization, feeds the normalization map, and then this goes inside X. So C is a curve inside some variety. I take a normalization of the curve. Remember, in general, normalization is not going to give you a smooth variety, right? You know that the singularities and normal varieties are in codimension 2. But for curves, normalization is the same thing as smoothing it, right? So this is a smooth curve that resolves the singularities of C. And then what we do is we take, so I've got my curve sitting inside here, and I can take, I've got a divisor D on X, right? I've got this map phi that maps my curve index, and I can take the pullback. That's going to give me a divisor on my curve. And it's what's that divisor on the curve? This is the divisor on C. And on a curve, we know the degree of the divisor is easy. This is a smooth curve. What's the degree? It's just a divisor is going to be a bunch of points with multiplicities, and it's just the sum of the multiplicities, right? So it's exactly this sort of picture that you have here's my big variety X, and I have my curve sitting inside X, and then I have some, this is terrible because I'm like in a surface, but here's my divisor D, and I'm just going to look at this, and there might be some places where it's tangent, and I get some multiplicities, right? So I'm just counting the number of points. So this is the number of points with multiplicity. So that's how we define it. And then proposition is that things behave as you want. So if D is linearly equivalent to E, then D dot C is equal to E dot C, and D plus E dot C is D dot C plus E dot C. So this extends to Q Cartier divisors in an obvious way, extends to Q Cartier in the obvious fashion. So what's the point? D dot C, if D is only Q Cartier, then what I do is I take a multiple so that it's Cartier, and it's just going to be, if say LD is Cartier, then I just take 1 over L times LD dot C. You can find the multiplicity that way. So it's again, this is exactly what you would sort of do if you were proceeding in the most naive fashion. All right, so Toric case. I don't know if there'll be any chalk left when I'm done. So here it is, proposition 6.3.8. If C equals V of tau is a complete T-invariant curve. So tau corresponds to something in sigma n minus 1 with Cartier, and let's say, here's the picture, right? So I've got my V of tau. This is a V of tau, right? This is one of the orbits, right? So a wall corresponds to, right, the T-invariant points of a maximum cone. These are just the fixed points of the torus action. Then this is the fixed curves are going to be these walls. So, and let's see. So I have some picture like this. Here's my wall, and then I have sigma and sigma prime. And now, what do I want to do? If D has Cartier data, M sigma and M sigma prime, right? So we got handed a Cartier divisor. We know that it has local data on our maximal cones. A T-invariant curve is corresponding to one of these walls. What do I want to do? So the thing is that what I would do is I take U, take a U in sigma prime intersect N, which maps to a minimal generator of the one-dimensional lattice n of tau equals n All right. So before I say, so I haven't done anything yet. The point is that if I look at n of tau, so what is this? I look at the span of tau. This is span of tau is going to be n minus 1 dimensional, right? So I've got span of tau is n minus 1 dimensional. I'm quotienting my lattice n by this. This is going to give me a one-dimensional lattice, right? So I've got a one-dimensional lattice here, and then I take some u over in here in this cone, right? That's going to map down. So sort of the picture, intuitively what the picture is we're kind of squashing this space, right? So I want to think of squashing tau. So tau gets sent to 0, right? And then what's left is this is my n of tau. Looks like this. It's a one-dimensional lattice. And I want to take somebody that's a minimal generator of this lattice. This is a lattice, right? So I've got these lattice points. So I take a minimal generator u over here. And then the definition, it's great, is that d dot v of tau is exactly equal to m sigma minus m sigma prime with u. We're going to do examples in a sec. So that's the definition. That's how we get this intersection pairing. And of course, we have to check that it satisfies all our axioms, but that's what it is. So it's, again, very concrete. So before we do some examples, I want to say a few more things. Say again. U is this guy down here. So what I do is I take a U and so U is somewhere up in here, right? And what I want to do is I want to take that U. Say, U might be this. So this is a big cone upstairs, right? So let's say this was one of my U's. This U, which visibly is not going to, this ray doesn't lie in my subspace tau. And if this was sort of, and if in particular, if this is a simplicial cone, I'm going to want to take something. Well, this ray is landing down here, right? But that U is actually upstairs, right? Okay. So m sigma prime. I can dot those with that U. That U is a minimal generator for the lattice downstairs. I mean, the U maps to a minimal generator. No, this V tau corresponds to this is the T invariant curve that corresponds to an tau and sigma n minus 1, right? So fixed points correspond to max cones, fixed curves are going to correspond to codimensional cones. Yes? A little louder. This is so David's point is that all the T invariant curves are going to be P1s because they are themselves toric varieties. And it's a one-dimensional toric variety. And it's complete, so it's just a P1.
In fact, in house picture where you have tau, you can see that you get the fan, the P1, because sigma.
I mean, this is this fan, yeah. So this fan. Or the fan down here is just going to be a fan inside, and this is the origin, and then I've got the rays going that way. So this is the fan of P1. So actually that's a good point, is that, so you might think, and it does illustrate that toric varieties are very special. So all these T-fixed curves are just P1s. We're not going to have, and you can have curves of higher genus, of course, sitting inside toric varieties. I mean, P2 is a perfectly happy toric variety, but those are not going to be some of the T invariant curves. The T invariant curves, just like in P2, right? So in P2, where we know our big torus, the only T invariant curves correspond to these things, and sort of if you thought of those, the way that we sometimes draw projective space with the coordinate points, 0, 0, 1, 1, 0, 0, 0, 1, 0, right? We have the coordinate lines, and the three T invariant curves are corresponding to the three coordinate lines that connect these things. So there's just not that many there's lots of curves in P2, but there's not many T invariant curves. In fact, there's 3. So you still look unsatisfied. Okay. So two general definitions. These are general. DNF. So, good. So this is, we haven't used, I was afraid that I'd started using NEF before its time, but we've talked about base point freeness. We haven't talked about the NEF condition. So D is NEF if D dot C is greater than or equal to 0 for all irreducible complete C contained in X. This is numerically effective. And base point free. So this is a general fact that base point free implies NEF. And roughly speaking, the idea of why base point free implies NEF is the following. It's pretty, a lot of this stuff seems very abstract, but it's intuitive. So base point free divisor, we know it actually gives us a map to projective space, right? And so what's going to happen is that if I have some curve sitting on my variety X, and I map it to projective space, either the divisor, when I restrict to that curve, is actually ample or very ample, and the curve actually has an image, which is a curve, and then I'll have a degree, and so that degree is exactly going to be this number. Or what could happen is that curve gets squished down to a point. The point is that because I have a base point free map, everything I don't have things where the map is undefined, right? Everybody gets sunk somewhere. So that curve, if it doesn't get sent to another curve, it gets squished down to a point, and it has degree 0. And so that means that D dot C is actually equal to 0. So that's the intuition of why a base point free divisor is going to give you something F, roughly speaking. All right, so those were two general definitions, or properties. I guess this is a prop, and this is a def. And then theorem. Let's do some torics. So D dp F implies D nef. Actually, these are if and only ifs. This one is from there. This one is going to come from D dot V of tau greater than or equal to 0 for all tau element of sigma n minus 1. So to prove this, we go like this, and like this. And I
Generally speaking, you have to say it's an interior wall, so it's not all cones of sigma n minus 1. You know, it might be on the boundary of the thing.
Well, the point is, the point is that there's hypotheses missing here. So we want this to be a nice case. So the nice case is called sigma is convex and full dimensional support. And these are going to be the interior, as David said, interior walls. So in particular in the nice case, when we have a complete fan, then this is for all those things. So what's the proof? I'm going to only prove this part, because it's nice. So by 6.1.7, which I hope is still on the board somewhere. No, 6.17 is long gone. That's from the first hour. By 6.7, it's enough to show. We want to show that phi sub d is convex. Right? I want to prove the base point freeness. We know base point freeness corresponded to being convex. And so by 6.3.8, which is on the board, so 6.3.8 is telling us how to do the intersection pairing. So by 6.3.8, d dot v tau is m sigma minus m sigma prime, comma u. Has to be greater than or equal to 0 for an appropriate u. And that's saying exactly that m sigma u is greater than or equal to m sigma prime of u. But remember where u was. U is sitting inside, this is the Cartier data, u is sitting inside this cone, right? So that's an equality, right? So this one is equal to this is equal to the phi sub d of u, right? Because this is in the cone of sigma prime, and so and then so what? U is not, of course, and U is not in sigma. Because if U was in sigma, you would be in sigma intersect sigma prime, and we know that sigma and sigma prime get squished to 0, right? Let me say it again. So we know that this U is in sigma, my U is in sigma prime. It's not in sigma, because if it was in both sigma and sigma prime, that would mean, remember, sigma prime are going to different sides of this little thing. So to be in sigma inter prime would mean that U gets squished to 0, right? Because so U is not equal to 0. And so that means by 6.1.5, this says that we're convex. This would be is convex. And that's the end of the proof. So, so we have this nice, so what's the point? Again, we have a really nice condition for base point freeness and nephness in the toric case, which is just checking on the maximal faces. So, and let me put a little toric climate. So 6.3.13, this is called the toric climate. This is that sigma complete. Then D is ample if and only if D dot V of tau is strictly greater than 0 for all tau and sigma n minus 1. So again, the intuition for this, so one direction is easy and intuitive, and that is that if D is ample, some power that's very ample, some power of this times V of tau, this is going to be exactly the degree of the corresponding curve in the projective embedding, and it better be a positive degree if you've actually got an embedding, because a curve has to go to another curve. So the content is sort of in going the other direction. And in particular, the beauty of this is in the toric case. I mean, a priori, if you say that, you know, for all complete irreducible curves, that D dot that curve is positive, you're screwed. There's billions of curves. I feel like Carl Sagan. There's billions of them, right? But here you only have to check on a finite set, right? That's what's so great about everything here. So, all right. So numerical equivalence, some definitions, X1. I'm going to use this symbol for equivalence in the interest of brevity. A divisor is numerically equivalent to 0 if it acts like whenever I nail C with it, I get 0. So every curve, when I do the intersection pairing, I get 0 with D, and D is numerically equivalent to 0. And the numerical is just because this is a numerical condition, right? And as you can get, and so if D is numerically equivalent to E, if D minus E is numerically equivalent to 0. Here's a nice prop in the toric case. So there's a lot of subtleties that are going on in general here, but in the toric case, everything is nice. So sigma convex, full dimensional support. Then D is numerically equivalent to 0 exactly when D is linearly equivalent to 0. So how nice is that? So all the subtlety of numerical equivalence in the toric case is just saying that D is linearly equivalent to 0. So now some objects that we're going to need. Z1 of X is the free abelian group, gemmed by star, by our irreducible complete curves, and a definition. So if C is in this group, we say that C is numerically. So now we do sort of we're flipping back and forth between divisors and curves. So when's a curve going to be numerically equivalent to 0? Exactly when you think it is. That is when I do the pairing of C with all my divisors, I get 0 if C D dot C equals 0 for all Cartier D. And then C is numerically equivalent to C prime, exactly when C minus C prime dot D equals 0 for all Cartier D, right? So I have this notion of numerical equivalence, which basically says when I do the intersection pairing, I get 0. And I have the numerical equivalence both of divisors and for curves. And so, as you can guess, there's a nice pairing. So let's see. So there's a pairing from Z1 across Cartier div by taking a curve in the Cartier divisor and sending it to the intersection product, and it goes to Z. A couple more definitions. You guys have to bear with me. I'm sorry. I know we're right before lunch and lots of definitions, but we're going to do some nice examples in a second. So N1 of X is C div mod. So I take Cartier divisors, kill off this numerical equivalence, which for us is just linear equivalence, right? So this is Cartier divisors up to linear equivalence, which is just Cartier divisors. And then I tensor it over Z with R. So this gives me a real vector space. And I do the same thing for my curves. So now I have two real vector spaces, and this is where my cones are going to live. And so that's the last definition, I think, for a bit. This is 6.3.17, and finally 6.3.18. We get the Neff cone and the Mori cone. So the Mori cone, well, let me do it Neff first. The Neff cone is equal to the cone in N1 gen by what? All right, audience participation. What's it going to be generated by? It's the Neff cone. It should be generated by Neff divisors, right? Not at all obvious that it's cone, right? It should be cone. I get Neff divisor sitting in here, but it's going to be a cone. And E of X generated by, this one's by star, the irreducible complete curves. And then the closure, this is the Mori cone. This is the Mori cone. Is the closure of this cone. So this doesn't have to be a closed cone. The Mori cone is the closure of that thing. And so, what we're about to see, so we've got about 15 minutes left. On Friday, David gave us the notion of a primitive collection. And where we're going right now, if you're feeling like, okay, Neff cone, Mori cone, some abstract algebraic geometry objects, we're going to see that there's a really beautiful description of these things in terms of those primitive collections that David defined on Friday. So that's going to be the punchline in just a bit, but we still have a few more preliminaries before we get there. So, lemma. Not hard. Neff X equals N E of X. Check. Dual cone and E of X. Oops. So the point of this theorem is that there's a nice duality between the Neff cone and the Mori cone, and the the Neff cone is strongly convex, the Mori cone is going to be a full dimensional cone. So this says in some sense that these cones are all very nice. And now let's see, toric case. So 6.3.20 toric. I was assuming X was normal. I think that's the only assumption on X. Sigma convex and full support. Then Neff of X sigma is a rational polyhedral cone in PIC. And I think for time, I'm going to skip the proof. It's not bad. I want to say something else about this in the projective case. So if X sigma is projective, then Neff X and the E. So in the toric case, everything is as nice as it could possibly be. The Neff cone and the Mori cone are duals, they're full dimensional, and they're strongly convex rational polyhedral cones. So this is saying that for projective things, they're as nice as possible. And then D is ample, exactly when it's in the interior of Neff. So roughly speaking, what's going to happen is we're going to see that the walls of this cone are exactly going to, the walls of the Neff cone are exactly going to be the base point free divisors that are ample. As soon as you're in the inside of the cone, you're actually ample. So the walls are going to be given by basically your dot product, when a dot product with one of the v taus is equal to 0. All right. So an example, so if we do this, I'm not going to justify it, but for 6.3.23, if we do the Neff and Mori cones for the Hirzebruch surface, turns out the Neff cone, we've already seen this, right? So from this theorem, we know that the Neff cone is going to be the base point free divisors, and we've already calculated the base point free divisors on Hirzebruch, so that we're going to have a picture that looks like this. So this is one of these classes could be generated by D4, one's generated by D3, right? And so the point is, if I'm just on this ray or this ray, I get base point free, but I'm not ample, and as soon as I'm in the interior of this cone, I get ample. So, and we've actually seen this at least in certain examples with D4, even though I did D4 wrong. If I had done D4 correctly, we would have seen that we get this little polygon that looks like this, and clearly that guy doesn't give me the whole thing, so it can't be ample, right? So that's not in the interior. And for D3, we actually, I think, did this at one point. We get something that looks like this. So these guys that are on the boundaries are base point free, and as soon as you're in the interior, ample. And then when you do the Mori cone for this, you actually get something that looks like this. And we've got, right, we have 4 rays, right? So I have these 4 rays, and this was, I think, U1, U2. How did we label these guys? I think this was U1, U2, U3, and U4. And so this is V of tau 1 equals V of tau 3 here on this ray. Then this was V of tau 2. So I think this must be, I don't remember. Anyhow, check in the book. But the reason you can work through this, but the point is these don't look like dual cones, right? And so we're going to see in the next section how that happens. These don't look dual. So this is, there's like, the reason I put this example up was to put a little question mark next to it and say these cones don't look dual, but we can calculate them. And so that's what we're going to do in the last section, which is the simplicial case. where all these things are super concrete and nice. The other thing, I meant to say this, I think I said it to a student, so I taught basically the first 10 chapters of the Toric book in a year-long course, a year-long graduate course. And most of these things that David and I are covering in 2 hours of lecture, when I look back at my notes, it was either 6 or 7 hours of lecture. So we're going at a really breakneck pace. And so if you feel like you're getting discouraged, what I would say is don't get bogged down in reading the proofs of the theorems. Look at the examples and see how to illustrate the theorem with the examples, because that's sort of how you internalize things. So that was my sort of very brief pep talk about us moving at a very fast pace. All right, so 6.4, last section. So if you remember, I want to remind you of our little two sequences. So we have two sequences like this. So I'm going to assume sigma at least 6.4.1, sigma full dimensional and convex support. And in this section, everything is going to be simplicial. So in the last 10 minutes, it's all simplicial. So we have sequences that look like this. So this was the presentation for PIC. This is just the presentation for PIC, answered over Z with R. Right? So this is my presentation for PIC. You guys are all with me, right? This was M goes to my direct sum of the T invariant divisors goes to the Picard group, and then I tensor with R. So, and then we also have dually. I'm going to call this alpha and beta. And dually we have R sigma 1, beta star, alpha star, and N1. So the mysterious N upper one and N lower one in the toric case have these very concrete descriptions. And furthermore, the first thing that's super nice is, what is this space N1? This N1 is simply, these are real vector spaces. This is a concrete map. This map had the rays of my fan as the rows, right? So I've just transposed everything. So what this is, here the rays of my fans are columns, and this is exact. So this N1 is the kernel of that. So this N1 is simply relations on the rays. Right? So that's what this N1 is. So it's the space of relations on the rays. And then the last thing I want to say is if I have what's the pairing? So the pairing, right, these guys I have to be careful with duals, but the point is that I have a pairing between elements in here and elements in here, right? I want my Neff divisors and my curves, and I want a pairing, and the pairing between these two, I won't prove it, but the pairing between N1 and then lower one is just that if D is equal to some summation A rho, D rho, that's somebody over here. And if R, a relation, is equal to some summation B rho, U rho, notice these correspond, right? This is one of my relations. The pairing is the nicest possible thing it could be. Then the pairing is just summation A rho, B rho. Is the pairing between these things. So everything, I'm not proving this, but the proof is actually pretty straightforward. And I wanted to say one little thing about how do you actually compute? So we have this nice pairing, but how do we compute? How compute? I beg your pardon? I'm not understanding your... Is it okay? Okay. Okay. How do you compute dp? d sub rho dot c. We already have a theorem, so 6.38 gave away one way, but we're going to get another way in a second. But first I want to do a little observation. First, this is what we're going to do next, but first an observation. If I have an irreducible curve C by 6.4.1, and irreducible curve C gives element of x sigma, gives summation over rho, d rho dot c of u rho equals 0. So when I do this, pairing for an irreducible curve, I get this relation. And so you can see this actually directly. So this was from 6.41, but how do we see this, that I have this relation? So to see this relation, I've got summation m comma u rho d rho is equal to divisor of chi of m, right? You hand me some character, that character has a divisor, and the divisor is what I get from this, right? Everybody's with me on this. Divisor of character looks like this. So in particular now, if I just take this relation and I bang it out, then I get exactly summation m u rho d rho c, because this is going to be 0 is right in pick. This is 0. It's the divisor of character. So this is the 0. This is the divisor of character 0. So I get this is going to be 0 and this is for all m, right? It's for all characters m, right? And you hand me any character, this relation is going to hold. And so the point then is I regroup this as a nice little pairing, as this is m comma summation of d rho dot c u rho. So if I have this pairing being equal to 0 for all m, as long as the m span my lattice, the only way that can happen is for this thing to be 0. So I get this nice other way to see that this relationship holds. So this is 0 for all m. Which implies that. So I think that's just a cute little aside, which is why I wanted to do it. Anyhow, so let's see how to do these intersections. I want to compute d rho dot c, and David has been making mea culpas for going a few minutes into lunch, so I want 5 more minutes. Can I have 5 more minutes? That was reluctant. Yes! We want to see how to do the pairing. Come on, this is fun. Doing the actual pairings. If I said the next 5 minutes I'm going to be doing a lot of, I'm going to start doing what I'll be doing Thursday night, which is a turbo review of spectral sequences. I could see why you guys might say, we don't really want to see that. But this is how to do computation, so this is fine. So we're in the simplicial case, right? So here's some nice simplicial fan. I have sigma, sigma prime. And I have rays. Let's say this is rho 1, rho 2, up to. This is in general a high dimensional cone, so let's say this is an n-dimensional cone, and then u sub n plus 1 over here, right? So here's my picture. And here's tau. This is my face tau. So multiplicity def, the multiplicity of a simplicial cone, gamma with u1 through uk min gens, is defined as the index of, as you would expect, z of u1 through k in n intersect span of u1 uk. So you hand me a bunch of ray generators. They might not span a smooth cone, right? The index, or the multiplicity of that cone, is by definition the index of, this is a sublattice. I look at n intersect the span. This is a real vector space. I intersect my real vector space with n. I look at the span of that in here. That's the multiplicity of a cone. Okay, so I needed that definition. And now the thing is that since u1 up to u sub n plus 1 are linearly lin dependent, there exists some relation. Alpha u1 plus summation 2 through n, beta I ui plus beta u sub n plus 1 equals 0, right? Got to be the case. I have n plus 1 vectors in an n-dimensional vector space. So I've got this relation, and I can assume that alpha and beta are greater than 0 because they're on opposite sides of the cone, right? Alpha and beta are on opposite sides of that wall. Okay, so here's the recipe for intersecting. And this is, notice, this is unique up to scalar because the U1 through, these are independent, right? So up to a scalar, this relationship is unique. It's unique up to scalar. So then here's the prop. Okay, so this one's not so surprising. I have my curve here. This curve is lying on these two, it lies on these two charts. In particular, right, this is a P1, it's sitting in here. How's this P1 going to meet one of the other D rows? It's only going to meet the D rows that are over here, right? So I never meet any of the other ones, so this one is unsurprising. B, how does it meet? So what do I have to do? I only have to worry about these rays. There's a symmetry, so I have to worry about what happens at the ray that doesn't touch tau, and I have to worry about what happens to one of the guys that's on tau. So d rho 1, or yeah, d rho 1 dot v tau is equal to the multiplicity of tau over the multiplicity of sigma. Very nice recipe. And finally, d rho I dot v of tau, if this I is in 2 to n, is going to be equal to b sub I times the multiplicity of tau over alpha times the multiplicity of sigma. And that's equal to, if you're so inclined, this is the same thing as b sub I. There's a symmetry, so b sub I of multiplicity tau over beta multiplicity of sigma prime. So I want to do an example of this for, of course, the Hertzsprung surface. So let's see what this looks like for Hertzsprung surface. So 6.4.6. And let's make it super concrete. Let's say that this is minus 1 comma r. So what's our wall relation? We get the wall relation here is exactly this plus this is 0, right? So I get U2 plus 0 U1 plus 0 U. I'm doing the wall relation on U1. Let's do all these U2, U1, U2. So the wall relation for U1, this is my U1, right? Here's my two cones. So I get U2 plus 0 U1 plus U4 equals 0, right? This plus this is 0. Here's the wall. I have this, right? So that's my wall relation, so it's straightforward. And so when you work this out, this says exactly that D1 dot D1 equals 0.1 over 1.1, which is 0, okay? So that's saying that this divisor, D1 is the corresponding divisor. This has self-intersection 0. Right? So when we do this for U2, we get U1 minus RU2 plus U3 equals 0. This says D2 times D2 equals minus R dot 1 over 1.1 equals minus R. This is, oops. So here's one of these examples of a curve that has a negative self-intersection, right? The typical example, so exercise for you guys to do yourselves, if you took P2 across P2, this is a fun little one. So you should do this over lunch. Here's P2. If I add in this ray right here, right? We know that this ray is blowing up at a T invariant point, right? I'm still going to have a nice, you guys are all with me on this, right? This is blowing up at a T invariant point, and we know from whatever Hartshorne chapter 5, section 3 or something, that when I blow up a point here, I should get a curve with self-intersection -1. So what you should do the same thing I'm doing here. This is going to be the Hirzebruch surface H1 instead of H2, and check that you get a curve when you do a blow up with self-intersection -1. So, and then finally, if you do, say, if you do something, check, say, D2.D3, you can easily check that this has self-intersection 1. And that's not so surprising because D2 and D3 are lying in the same chart. This is just a nice smooth C2, and you can see that they're meeting transversely, so they should have self-intersection 1. And in fact, if you work through this, you'll see that D sub I dot D sub I plus or minus 1 is always 1. So, that's the end of that example. I want to say I'm already 10 minutes over time, but I want to write down one last formula because I mentioned primitive collections. So I actually ended, I think, about 20 or 30 seconds early on most of the first lecture. So I'm collecting all my overtime pay right now. So this is last 5 minutes primitive collections. So remember, a primitive collection is a set U1 through UK such that U1 through UK is not contained in a cone in any sigma element of sigma, but all proper subsets are. And in some sense, so that says that this sort of defines a minimal non-face of sigma. So that's a primitive collection. And so the theorem, two theorems, I guess, X sub sigma projective simplicial. Notice we've already seen simplicial varieties, smooth simplicial varieties that are not projective. That was the first example at the start. But if this is a projective simplicial toric variety, and D a Cartier, then D is NF. Another condition, if and only if phi sub D of the summation of the U rows for a primitive collection is greater than the sum of the phi sub D of the U row I for a primitive collection, for all primitive collections. So in particular, to check nephness, it's sufficient to check nephness on all primitive collections, and it's ample if this is a strict inequality. So this is a beautiful criterion, and I want to close with a last theorem on what the Mori cone looks like. So, def 6.4.10. Let's say P is a primitive collection. PC is a primitive collection. So if PC is a primitive collection, then summation I equals 1 to k of rho I is in the interior of some gamma. You guys with me? Right? If I add all these things up, that's going to have to lie in the interior of some cone, right? It can't lie on a face, because if it lay on a face, then those things would be contained in that face, and then I'm not a primitive collection. So what? So the point is that there exists unique primitive relation. Summation I of this is equal to summation P in gamma 1 of C row U row, right? It lies in the interior of this cone gamma, so I can write it as a combination of the rays of gamma. These C's are all going to be positive, right? Because it's in the interior of the cone. So this,
you meant to say first line the summation of the U row I.
Yeah, I did. Sorry, my bad. I want the primitive generators of the rays. And the C's are greater than 0. So the theorem is what's the Mori cone? theorem, the Mori count of a projective simplicial toric variety is equal to summation P, a primitive collection, of R greater than 0 of R of P. So what is this? P is a primitive collection. What is this R sub P? So I have to tell you what R sub P is. RP is equal to a vector of betas, rho and sigma 1, which is defined as follows. It's 1 if rho is in P, in my primitive collection. I guess PC I should have used. So I have a primitive collection. It's 1 if rho is in the primitive collection and not in gamma of 1. It's 1 minus C sub P. C sub P are the coefficients up here. If P is in this and P, that was not, and P is in gamma of 1. It's minus C sub P if P is not in the primitive collection, but is in gamma 1. And finally, it's 0 otherwise. So I apologize for going over time. This might not strike you as appealing because I haven't done an example, but the point is that the data of these of the primitive collection gives you a primitive relation. The data of the primitive relations is enough to define the Mori count, and it's defined in exactly this way. So there's a very nice and concrete description of the Mori count, and that's a good place to end. And like I said, mea culpa for going over time.